Hey everybody, welcome to the last video for the 2019-2020 school year in Statistics 2, where in this video our intention is to wrap everything up, talk about the different things we've discussed, and also talk about how it all fits together and what we ultimately want you to take away from this course as you move on. So let's remind ourselves what statistics is as a practice. So at its very core, statistics is using information from representative samples in order to infer information about larger groups. As a reminder, when we can collect information on a whole group, we call that a census. For example, the United States government has a Census Bureau, whose job is to try to collect information on literally everybody in the country. But if we can't collect information on a whole group, we must do the practice of statistics. And there are two main parts to statistical reasoning, and we have done both parts in different times in this course. The numbers that we compute and the meaning that we give them. And we cannot understand a statistical conclusion fully without knowing both of those parts. So in other words, as an example, we might compute a p-value, but then we give that p-value a meaning when we draw a conclusion about a hypothesis. So what did we talk about in this course? Well, at the end of Statistics 1, we talked about correlation and regression when we did the Barbie or wrestler drop. And correlation and regression was about collecting data and predicting relationships between two quantitative variables, such as rubber bands and fall height. We talked about probability, which is understanding the theoretical chances of something happening. We did confidence intervals for proportions and means, which is using a statistic to estimate a parameter. We talked about inference tests on proportions and means, which is testing a statistic against a parameter. And last, we did inference tests on differences between two proportions and two means, which is testing a statistic against another statistic. And each of these topics has to do with inferring relationships and making predictions. So why does all of this matter? Well, we use numbers to communicate all the time, and we may use those numbers to communicate by summarizing features, like what is the mean of something, perhaps to understand relationships, like when we did regression, or to predict outcomes, which is what we're always trying to do in the various sciences. However, often numbers are used in a manner that communicates precision that we don't actually have. This occurs very frequently. Like, for example, you go to the store and a bag of chips tells you that it has 10 ounces of weight. And you take that, and most of the time you read that and go, okay, this bag is 10 ounces. What's more likely to be true is that, well, most bags will be very close to 10 ounces, but there's going to be some variability. And occasionally you'll get a bag that's further away from 10 ounces. So there's a precision to that measurement that isn't actually there, but we just sort of take it for granted that it's there. And where in your life are numbers used to communicate precise information? For example, food and nutrition. You may be wondering how many calories are in a slice of pizza. Or survey results, like you may be looking up how many voters support a given administration. Or economics, you might want to know what our current national GDP is. History and sociology, you may be curious how many people died in the Black Plague of the 14th century. Or in the natural sciences, there are too many questions that we would want to know the answers to. And in each of these cases, we may want to get absolute precise results in numerical form. But let's just take an example. So I'm just going to do a Google search on how many slices are in, or how many calories, are in a slice of pizza. I know how many slices are in a slice of pizza, so let's actually Google this. How many ounces in a cup? I know that. That's 8. How many calories are in a slice of pizza? So I'm going to Google that, and let's see what happens. 285. 285 calories in a slice of pizza. Now it does specify 14-inch regular crust and one slice being 107 grams. So first of all, Google is imposing precision we didn't necessarily give it. We didn't tell it how big a pizza was, what kind of crust, or how big our slice is. So it's giving us that precision because it needs that to give us an answer. But even then, think about still all the variables this isn't accounting for. How is the crust made? It says regular crust, but what does that mean? Cheeses, different types of cheeses can have different calorie counts. Even different types of mozzarella have different calorie counts. How is the sauce made? How much oil was used to make the sauce? How much sauce was put on the pizza? So even though Google tries to give some precision here, this is still very much an estimate. Realistically, it's probably the center of some, or near the center of some confidence interval. That is really a better answer to this question. But I asked the question, it gave me a precise answer, and I want you to think about, before taking this class or having this conversation, how many of you would have looked at this, might have looked this up and come away with, okay, it's 285 calories, without thinking about how could they really be that precise and what factors are we not taking into account here. So that's just an example, but all of the questions that I posed on the previous slide are questions for which we might think there's a precise answer, but more often than not, there's just an estimate that is going to have some margin of error based on the data. Statistical reasoning comes with a lot of pitfalls. And recall we said there's two parts to statistical reasoning. The first part is the numbers that we compute. But when we compute numbers, we need to wonder if our computations are valid based on how we're doing it. Are they correct? What if we put in the wrong number in our calculator, as we do sometimes? And then are the practices and theorems that we're using to do the computations even justified? That depends on what we're actually doing. And then we give those numbers meaning, but when we do, we have to ask ourselves, was our sample representative? That will determine whether or not the numbers even mean what we want them to mean. Are we possibly oversimplifying our result in how we're interpreting the numbers? And are we inferring things that the numbers don't necessarily mean? I see this happen all the time with people trying to give too much meaning to a statistical result. We have to remember that human reasoning is filled with heuristics and biases, if you recall that from one of our past videos, and bad statistical practice can reinforce those heuristics and biases. So I don't want to be overly negative, so let's talk about the silver lining, and that's that good statistical practice can help us overcome those heuristics and biases. And with the help of statistics, we are learning more and more about biology, geology, paleontology, epidemiology, psychology, chemistry, physics, and this is just to name some of the sciences that we are using statistics in to learn more and more information about. And around the world, despite how everything can look from time to time, from a lot of statistical measures, the quality of life of everyone on the whole is improving, and knowledge from statistics has helped make that happen. But what should you as a whole end up taking away from this course? Well, for one thing, I want you to take away that this course has only scratched the surface of statistics. This is a very introductory level course. Statistics is a modern, growing field. For example, there's big data, which is the statistical field of what do statisticians do when instead of having a small sample to represent a big data set, they actually have a very large sample to represent a data set. Now that we have computers and more efficient ways of collecting information, statisticians have to work with bigger and bigger data sets, and that presents new questions and challenges. Bayesian statistics is a new way of looking at the process of inference and what it means. And some proponents are even suggesting that we stop using p-values, which were a major component of the course you just took. And machine learning and artificial intelligence are major branches of statistics that are building right now. The other thing we want you to take away is not just about statistics, but the thinking overall that goes behind good statistical reasoning, which is what we call critical thinking. So what does it mean to think critically? Well, for one, you should be thinking more about the information you get every day. How good is the evidence behind that information? Sometimes you know, sometimes you don't, but it's always good to ask the question. Now, a lot of people agree with that statement, or say they do, but the next one is a little more challenging. Scrutinize your own conclusions and beliefs. How good is your evidence for all the things that you say and believe on a day-to-day basis? That's just as important as thinking about the information that other people give you. We all think things for different reasons, and it's a good reflective practice to think about how good our own evidence is for all the things that we hold close to us. But on top of all that, having a positive growth mindset when it comes to learning. Skepticism, which is just the practice of being critical about information you hear and information that you have and believe. Skepticism is not the same thing as cynicism. It's always about striving to learn. Remember that the most useful information to everyone is the most accurate and correct information. We ideally don't want to just know things, quote unquote, that are true enough for us to get by and maintain our worldview. We ideally want to know things that are most likely to be objectively true. So I sincerely hope that you have gotten a lot out of this course, that it's made you think a little differently, a little more deeply. There's so much more to learn about this subject and related subjects. I encourage you to look into things, to read, to question, and to always have that open scientific mindset. And want to learn more about the world around you and how that learning can enrich in your life and the lives of others. And with that, I hope you've had a good school year. Hope you have a good summer, and think deeply and critically in everything you do.